Last time we talked about, this is green, I don't want that. Okay, what did we do last time? So we talked about, oh yeah, we did like floating base dynamics in 3D. Kind of in maximal coordinates. That was kind of the big thing last time. And we talked about sort of the maximal versus minimal coordinate stuff a bunch. And then we did variational integrators. In maximal coordinates. And kind of the basic story there, right, is that most of the things that you'll hear about, minimal versus maximal coordinates are probably not true. And most of the issues classically with maximal coordinate type methods are kind of magically resolved if you go to like a variational integrator that respects the constraints by construction all the time. And they work pretty well, pretty good. Okay, so that's any questions about any of that stuff? So we did this whole maximal versus minimal thing. And there's interesting trade-offs there. Pretty much all the current simulators use minimal coordinates or, more or less minimal coordinates, like Bullet and Drake and Mujoko and stuff. There really aren't any, like what would be considered kind of state-of-the-art robotic simulators that use maximal coordinates. A bunch of recent-ish simulators that are like for GPUs and stuff have tried this. Like I think Brax is maximal coordinates and stuff, but their physics is really bad. So they're probably not worth it. Worth looking at. Okay, so today we're going to talk a bunch about so-called fast, in quotes, dynamics algorithms. And as with many topics in this course, this is very much my take on this subject. That is not what you will hear from other people. And take it with a grain of salt if you like, whatever. It's not wrong, but it's just my opinion about this. And I have lots of opinions. Okay, so what do we mean by fast? That's the first kind of, in this context, what does fast mean? And so a lot of you probably heard about these things, right? So the basic story here is that classical like Lagrangian mechanics stuff, or manipulator equation stuff, etc. If we write that stuff down in a way we've done, so far in the class, it requires order n cubed floating point operations. To compute your accelerations. And this n is your number of degrees of freedom. So as you can imagine, if you got a pretty big complicated robot, like a, I don't know, like a 30 plus degree of freedom, humanoid type thing, this can start getting pretty expensive. If you start looking at, really like discretized, sort of like models of flexible things, it starts to get pretty gnarly. And so where do we get this? I've mentioned this a couple times, but just to sort of make this, one more kind of look at this and where this is coming from, it's really simple. It's literally just, if I have the manipulator equation, or the Lagrange equation, whatever you want to call this, roughly it looks like this. We got my mass matrix, my sort of Coriolis dynamics biasy thing, my forces for control inputs, whatever else. If I want to solve this for accelerations, I got to solve it for V dot. I have to invert the mass matrix and solve a linear system. So I end up with this sort of thing. I got to do M inverse times like the F minus the C. And this is just solving a linear system with an n by n mass matrix. If I'm in minimal coordinates, right, the mass matrix is n by n. And hopefully we all know that solving linear systems with an n by n matrix is an n cubed operation, right? And that's it. It's literally just that if you write this down kind of in the naive standard way, you have to invert the mass matrix. And therefore, you're solving an n by n linear system, which is order n cubed. This assumes, by the way, yeah, that it's like just a dense matrix, right? Which is usually the case in minimal coordinates. So that's kind of all there is to do, right? There's nothing else. It's a dense matrix. You got to invert it. There you go. So the other things I'll mention about this is that, so this is just for computing the accelerations. It turns out doing, all the other dynamics things like forward simulation, discrete time stuff, using explicit Runge-Kutta or implicit Runge-Kutta methods or variational integrators, all of them scale cubically, in case that's not obvious. The reason is, right, if I want to use RK4, I do like 4 dynamics calls per time step. So that just changes the constant in front of the n cubed, right? Like it'll be 4x, whatever it is, just for a single call. If I use a variational integrator or an implicit integrator, I have to solve a Newton thing, right? So what happens there? Inside the Newton method, I'm solving an n by n linear system again, right? And so it's the same cost. And the trick is there, like you only ever need a finite number of Newton iterations, usually 3 or 4. So you can bound that. So again, that's just a constant out front. You have to solve like 4-ish n by n linear systems. So again, all those things just change the constant out front. So it's always n cubed, kind of no matter what you're doing, whether it's just doing this or if it's doing a simulation step or whatever. Yes, let's write that down. Okay, so there's that. Okay, cool. So that's the minimal coordinate story. The maximal coordinate story, if we're like similarly naive about it, is even worse. Let's write that down really quick. So here we're solving a linear system at each time step as well, but we have a much bigger linear system to solve. And I'm gonna like cartoon write this down for now, where we have some big like I guess let's call this we'll call this like, this is like that M bar thing, right? The giant M with all the mass properties of all the bodies. And then we have our joint constraint Jacobian stuff here. So we have this KKT system, and we're solving for both the X's and the lambdas. And we've got, some right-hand side stuff here that's like our dynamics biasy stuff and our constraint violation-y stuff. So this, we just have to solve this linear system. This is a much bigger linear system. This guy is, this is like, now n bodies plus n constraints cubed, right? So this is really kind of terrible in that, like, if I, in the minimal coordinate story, if I have fewer degrees of freedom, with lots of constraints, it gets cheaper. Here, if I have fewer degrees of freedom where I add more constraints, it gets worse, which is kind of interesting. And there actually is like a sort of trade-off point between these two, where like, if you have lots of degrees of freedom and few constraints, this one's cheaper. And if you have like lots of constraints and few degrees of freedom, that one's cheaper. It's kind of fun. So there's usually like a cutoff point where one becomes better than the other. But anyway, okay, so this is bad, right? So they both have this cubic flavor in kind of the number of bodies or degrees of freedom or something. And the overall message is that when we say fast algorithms, we basically mean anything that beats this n cubed complexity. And in general, you can, well, so in general, it's always n cubed in the worst case, but for a lot of robotic systems that we care about, namely things that are mostly serial chains or open chains that don't have closed loops. We'll get into this in a little bit and explain this in detail, what we mean. You can achieve results much better than this. And in the best case, really simple, like chain-like things, you can get this down to order n instead of n cubed, which is much, much better. That's a huge, huge difference, right? So that's what we mean by fast. The terrible 3. Okay, so that's what we're going to try to figure out. So there's lots of variations on this theme. You probably all heard of like Featherstone and like recursive Newton-Euler. I will say a couple of things there. One is that those ideas really predate the 80s vintage Featherstone stuff. They go back a lot further, and there's lots of like sort of similar ideas in other adjacent fields, namely in control and stuff. So the ideas have been around for a long time, and there's a lot of sort of cross-pollination-y things where these have kind of popped up independently at different times. So I think the easiest way to see this, how this works, and like that it is possible, is to look at it in maximal coordinates. So we're going to do that first, and then maybe like I'll tease a little bit about how it looks in minimal coordinates, a la RNEA and stuff like that. So the name of the game here is sparsity structure. We're going to talk about, basically what we're going to do now is like zoom in on that KKT matrix and look inside the blocks and see what that looks like. We're going to do a particular system. So this is what it's all about. So let's look at like a multi-link pendulum. Ugh. Okay, so let's say for now, for fun, let's say I've got like a 3-link pendulum. So I'm gonna have something like this. And let's say I've got, links numbered 1 through 3 and joints 1 through 3. Should color these guys. Cool. So 3 links, 3 joints. If I write down that maximal coordinate KKT system for this guy, I'm going to write it down in like a cartoony simplified way. So we're not going to write out like all the gory details of what's inside these. I'm just going to write out the pattern of it. And we're going to like just, yeah, let me do it real quick and we can talk about it. So, so we've got a big matrix with so we've got like M1, M2, 3 for the 3 links. And then the important thing, so that's block diagonal and very sparse, kind of obviously. And then let's look at these constraints. So this thing also has nice block structure. If I think about the first constraint, that's bolting me to the world frame, right? So it only depends on, I guess I should write the other side of this kind of vector over here. We've got like, your accelerations. So v dot 1, 2, and 3. And then we've got Lagrange multipliers for each constraint. So we've got lambda 1, lambda 2, lambda 3 for each of those joints, right? And, obviously we've got the MA stuff. And down here, we've got these constraints. So the first one, it's bolting you to the world frame. it only depends on the accelerations of the first link, right? So that block just shows up in this spot. So and I'm going to label these in a particular way. So subscript is for the link that it is connected to, or the constraint that's connected to, or the link. And then the superscript is going to be for the constraint. So here's what we've got. We've got C, I, J, where the I is the constraint and the J is the link. Okay, so this is C11. It's the first constraint, and it only touches the first link. And then the whole rest of that row is zeros because it doesn't affect anything else. The next constraint is this one. This one couples link 1 and link 2. So it's going to have two blocks. It's going to have C21 and C22. Make sense? So we got C constraint 2, link 1, C constraint 2, link 2. Cool. Okay. And it doesn't touch link 3 at all, right? Last one, constraint 3 touches links 2 and 3, doesn't touch link 1. So we're going to have blocks like this. So this is constraint 3, block 2, or link 2, constraint 3, link 3. So I don't care what's inside these right now, but all I care about is, and this is like really like topological properties, right, of the system. And there's this whole like idea of matrix sparsity patterns is actually like basically graph theory. This is like deeply connected with graph theory. And so like what's really going on here, like the pattern of entries in here actually corresponds to like the graph of this system, like how the links, and if you imagine like the joints as nodes and the links as whatever, right? You get the idea. So that's kind of what's going on. And then this guy is the transpose of this guy, right? C transpose. So I'm just going to take this and do that with it. So that looks like. So we get C11 transpose, then a bunch of zeros. We get C12 transpose, C22 transpose, and then C23, C33. Okay, cool. And then this down here is 0, right? And then the vector over here is going to have, we're just going to write down like a sort of generic version of this again. So these guys are sort of your dynamics bias, external force kind of things. And then these guys are your constraint, sort of your constraint violations, or in this case, these are like, doing this in continuous time. So remember, we like double diff the constraints and write them at the acceleration level. So this is kind of the acceleration story. And then this is sort of everything else that shows up when you double diff, right? We did this before. So the details don't matter here, just the pattern matters, right, for now. Okay, cool. And I guess the other message here is I did this just for the 3-link system, because that's kind of the smallest one where we can kind of like get some interesting stuff going and see what's going on. But the story here is that this block structure, so the block diagonal structure here, and this block banded structure where I basically have these two coupled neighbors, and then I translate down like this. These keep going. So this setup we're going to do right now will work for an arbitrary number of lengths n. So if I keep making this longer, all that happens is matrix grows, but the sparsity pattern is exactly the same. And this will keep just growing in that exact same way. Cool. Okay. Any questions about this? Oh, yeah. That. Oh, yeah. Okay. So these are big C's. These are little C's. This comes from, if I take a constraint, like if I have some constraint equation C of Q, like that says how these things are pinned together. What I do to write this down as like a continuous dynamics problem like this, I take this guy and then I differentiate it with respect to time twice. So I get partial C, partial Q, Q dot, right? And then I do this again and I'm going to get partial C, partial squared C, partial C squared, like a Q dot squared kind of thing. And then I'm going to get, and this is sort of terrible notation. I probably shouldn't write it like this. So you'll get that term. You'll get basically, if I take another derivative, I'm going to get, product rule kind of thing. So I'll get this term with the Q double dot with the same Jacobian. And then I'll get another term that's like the ddt of this guy, right? Equals 0. Okay, so this one is this stuff, and this one is this stuff. Make sense? Maybe I should use different letters for this. Let's use like D for this to make this more clear, and I'll clean the notes up a little bit. Here. Oh, thanks. Okay. So yeah. So you start with C of Q equals 0, then you get partial C, partial Q, Q dot equals 0, then you get partial C, partial Q, Q dot plus dt partial C, partial Q, Q dot equals 0. And then this is C, and this is minus D, I guess, from up there. That makes sense? Okay, cool. Okay, what's next? And then, yeah, kind of the note here is that the block structure sort of repeats for any number of links. Okay, cool. So now what we're going to do is learn how to do a sparse matrix factorization, essentially. And this is back to this like broader point of like tons and tons of algorithms that you've learned about are really just sparse matrix factorizations for particular sparse matrix patterns. Here's one. So we're going to invent a new, order n fast dynamics algorithm right now for the case of, an arbitrary n length 2D pendulum or whatever. So here's how we're going to do it. And this like general strategy pretty much always works. So the trick is to like look at this sparsity pattern and figure out kind of where the pattern stops in some. So where there's like a place where you end up. So usually you look at the corners. So in this case, what we're going to do is say, so see here where there's like basically this couples multiple variables. This one doesn't though, right? This one's just the end link. So this one I can like, basically bootstrap on. So the strategy is we're going to like take this one because it has fewer variables and like write this line out by itself and see what we can do with it. And then try to bootstrap a recursion. So we basically are going to try to solve this line and then plug it back in and work our way out the blocks in a sort of back substitution style fashion. This strategy pretty much always works with banded matrices. That's kind of the idea. You start on one corner and figure out some kind of recursive back substitution to work your way up. So we're going to do that explicitly right now, and I'll show you how it works. But this is a good thing to know about in general, and pretty much works on any banded matrix. So if you have a sparse matrix and you can like squish things around to get it to be like block banded in some way, you can pretty much always play this kind of game. And like so many algorithms are just this, with particular variations on the block structure. Okay, cool. So let's see. Yeah, the key to many, many fast algorithms is exploiting this sparsity. Okay, so let's look at that bottom right, like the last. So what we're really doing here is we're looking at the link 3 dynamics, right? That's what that row is that I showed you. The last link in the chain. And it kind of makes sense, right? Like the other ones have like 2 neighbors and like multiple things going on. This one only has 1 constraint. It's sort of the end of the line. So it has like a different sort of pattern, right? It's the end of the pattern. Yeah. Okay, so let's write just the last link out. So that's M3 V dot 3 plus this constraint Jacobian guy times the multiplier equals F3. Cool. Okay, so what we're going to do now is look at this thing and say, this thing's not square in general, right? We can't do anything with that. This guy is a mass matrix. This thing's always square and symmetric and positive definite and all that good stuff. So this is always invertible. So what I'm going to do then is I'm going to use that fact to solve this equation for this B dot in terms of everything else. And I'm going to get something that looks like this. And I wrote this in a particular way to emphasize that this term is some matrix times the lambda. This term is some positive vector. I'm going to name these things for notation simplicity and to make our lives less terrible. So we're going to call this whole matrix that multiplies the lambda big W3. We're going to call the vector over here little w3, such that we have this V dot equals big W times lambda plus little w. Cool. Now we're going to take this. I now have an equation for V dot in terms of lambda, and we're going to go plug this into the last constraint equation down here, that last row of the constraints, and see if we can bootstrap ourselves so we can now write things in terms of the next link, right? Basically that last row. So now I've got a thing that's like telling me, just the last link, and I can solve for the last link's V dot in terms of lambda 3. I'm going to now plug this in to this equation row, which couples link 3 to link 2. And this is going to let me kind of like start moving up the chain to link 2. That's kind of the strategy, right? So let's do that. So that equation on its own is just this. I'm going to plug in my result there for V dot 3 and eliminate V dot 3, right? So then I get this guy, and I can just move stuff around a little bit and solve this for lambda 3 in terms of V dot 2. Yeah.
Is that C3 or D3?
There's no D's anywhere, right?
Yeah, because I'm just confused because it changed from C to D plus.
Oh, shit. Yeah, I think I need to leave those as little C's. The side where I like, explained how the constraint thing works. I don't want to mess with the notation. Let's do this because it's going to screw me all up. We're going to call this D. So I don't because my notes all use C for that. And I'm going to continue making that annoying substitution everywhere for the rest of today because I didn't sleep last night and my brain is fried. So This is a safer bet. We cool with that? Okay, sorry about that. Yeah, the thinking on my feet thing is not happening today. All right, so that, now what? Okay, so yeah, now we're just gonna massage this and solve it for lambda 3. And again, this guy's non-square. It's not obvious from the way I wrote this, but this is symmetric, square, positive, definite, all the good stuff. You can tell if you go back to the definition of W here, this ends up being like this C3 guy times M inverse times C3, right? So it's basically a matrix sandwich with M inverse in the middle. It's symmetric, positive, definite, all the good things. And what's the size of this guy? It's square. What's the dimension? Is it the number of degrees of freedom? What is it? It's the dimension of the constraint. That's right. Because what you're doing is you got your mass matrix and you're smushing the constraint Jacobian on both sides, right? So that's basically like projecting you down into the constraint null space. It's like the dimension of the constraint. So in this case, if I'm in 2D and I have like 3 DOF per link and I'm doing pin joints, each one of those constraints is 2-dimensional. It's taking away 2 degrees of freedom, right? So this guy, in this particular case, it's a 2x2 and the ends are 3x3, right? Cool. Just to make sure we're thinking straight. Okay, so this looks like the following. Okay, so, and then once again, we're gonna like make up some names to make life better. So this guy is a matrix times V dot 2. We're gonna call this guy big S3, and this guy, which is a vector, little s3. So this whole thing now is big S3 times V dot 2 plus little s3. Cool. And so you can kind of see what happens now. So like I got some, I solved for V dot 3 there. I used that to like get something for this lambda 3. And this lambda 3 now looks like this. So now I've got something between, V dot 2 and V dot 3, right? So this V dot 2, if I know V dot 2, I can solve for lambda 3. If I know lambda 3, I can solve for V dot 3, right? So now I'm starting to get this recursion happening where I can like walk down the chain from top to bottom, whatever, right? See what's going on. So now I can just keep going. So unsurprisingly, the next move is, so I did, the dynamics equation for link 3 and the constraint equation for joint 3. Got this happening. Now I'm going to keep going. I'm going to do the dynamics for link 2, constraint for joint 2, and I can just keep going. And on the next round of this, it'll become very clear that it's a recursive pattern for these W's and S's. So we're basically doing a backward recursion up the chain from the end to back to the root. Okay, so next, right, we're gonna do just like keep going. So that one looks like M2V dot 2. And now this one has 2 constraints touching, right? Top and bottom. So you've got now 2 of these Lagrange multipliers showing up in here, 1 for each joint, right? And this guy has 2 joints. F3. I'm going to do exactly the same move. So I'm going to take the equation I just came up with for lambda 3 in terms of V dot 2. I'm going to plug it in here. And now I've eliminated lambda 3 totally from this equation. All right, because I wrote this in terms of V dot 2. So now I've got an equation that's just V dot 2 at lambda 2, basically where I started back there. And now I can bootstrap and keep trucking. right? So let's do that. So here we go. We got M2 V2 dot. This guy stays the same. Now we've got this thing. Then I can solve this guy for V2 dot in terms of the lambda. So I've got something that looks like this. It looks a tiny bit different than last time because we got this extra term now that sort of couples us to the next link. But otherwise, like structurally, it's exactly the same situation. So this basically modifies the mass matrix, right, for this link. Number 2, and then we get a term over here. So that's the matrix times the lambda, and then we get a vector term over here. I need to switch this over. So this F2 minus that's great. Okay, cool. Then we're going to play our same game. We're going to call this guy W2, big W2, little W2. So I've got, this whole thing equals big W2 times lambda 2 plus little W2. We're going to same game, plug this now into the constraint equation. So this one's now for the constraint that couples link 2 to link 1. And we're gonna play the same game, plug that in, so we eliminate v.2. And solve this guy for lambda. Yeah, sorry. Sorry about that, guys. We had a brief technical issue. But we're back now. Now I just need to make sure my iPad connects again. Hey, I did. All right, we're in business. Okay. Sorry about that. Okay, share screen. And we're back. I think. I hope. Okay, cool. So what we were doing, okay, we do this thing, we get this thing, blah, blah, blah. Same story as last time. You get some stuff. We're gonna like make up some new letters. This thing looks like this. Some other stuff. This one look like. Right, so this is like the same kind of thing here. And then. Okay, and now, going with the theme, we're gonna call this whole thing that multiplies the v dot. What are we calling this? S. And then this little vector over here, little s. So we get, this whole thing equals big S2 times v dot 1 plus little s2. Okay, so now it should be hopefully very obvious to all of us that we have like a nice little recursion going with these s's and w's, and I can just do this up the whole chain. It doesn't matter how long the chain is now. I can just do this until I get to link 1, right, and joint 1 all the way up. So here's the recursion. In general, you get like WK, the big one, equals this stuff. Little w is the same matrix. This stuff over here. Then we get the S's, which this. Okay. I've written lots of little wiggly indices that are nearly indecipherable. And, it's part of the learning experience. Deciphering, little squiggly K's and stuff. Makes you have to go back and rederive it yourself, right? It's good for you. Okay, cool. So now you got this thing. Now we bootstrapped it. We can go all the way up. Cool. Now, so the gist of this is I start at the base, the end link. I have like a weird, the bottom one is like a little bit weird and special, and I can solve that one because there's no coupling to anything else. Now I can bootstrap this guy, and you saw how that looks. Then what happens when I get up? So now I've got all these S's and W's. Now what? So what happens now when I get to the top? There's another special case. So at the bottom, we had a special case in the dynamics because this guy doesn't have any more coupling, and it's just like this base case here. When I get to the top, I have another special case, which is this first constraint, which only has one C instead of two C's. And that similarly lets me solve for the lambda 1 when I get to the top. And then basically, if I have lambda 1, I can bootstrap this whole thing. So I've got, if I have lambda 1, I can start plugging it into these guys and start heading all. So if I have lambda 1, I get V1, V dot 1. If I have V dot 1, I get lambda 2. And now I'm rolling and I can go forward and solve for all the V's, V dots and lambdas. That's what's going to happen next. So in particular, we use the first constraint equation, which is sort of a special case because it's just the one link by itself in there. We're going to plug in this thing that we just solved for in the recursion and get something that looks like this. Which we now have just an equation for lambda by itself with a vector thing. So we have a standard like ax equals b kind of situation. So we can solve this for lambda 1. Cool. So now we've got lambda 1. Now we're ready to go forward back to the backward pass. So we end up with, so now we have lambda 1, we can plug it into this guy to get v dot 1. Then we can use v dot 1 to solve for lambda 2 with this guy. And then dot, 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 all the way to the end where you end up with like, you get the general thing and you go all the way to the end with all your W's and S's. Okay, fun. Everyone cool with that? So you end up with a backward recursion for the W's and S's, like these matrices and vectors that you solve for. You get to the end, you can solve for lambda 1, and then you plug that in, and now you have a forward pass, goes back down, and plugs in alternately like lambda and v dot. So okay, to go and get all of the constraint forces and dynamics, right? And that's it. Okay. Questions about that? So literally this comes from just like staring at that sparse matrix and essentially doing back substitution up the blocks and back down again to like, which is extremely common trick. Like usually the fact that it's just this back substitution thing is, not usually super apparent, but you might hear this called like the Riccati equation sometimes in some contexts, or recursive Newton-Euler sometimes, or there's lots of names for these things, right? Anyway, cool. Now the question that we started with is, what is the complexity of our algorithm now? So now we have a new algorithm for solving this thing with a giant sparse matrix. Let's look at the complexity. You can probably guess what it is, but I will explain to you how you get this. So here's like, the equation that we got before. I should just copy and paste it. That's too complicated. See if I can do that. Probably going to take me longer to do that than to just write it again. Okay. See if I can. Copy and paste works. I hope. Yeah, this is definitely more trouble than it was worth. I think there's some annoying thing where it's like, go across pages or something stupid like this. Copy worked. Paste. Hey, look, it worked. Okay, great. Definitely was longer than writing it. Okay, anyway. Okay, so if I look inside this thing, I'm solving this linear system, right? This matrix in here, how big is this matrix? If you're in 3D, it's 6 by 6, because it's just a mass matrix for a single rigid body. If you're in 2D, it's 3 by 3. Whatever, it's a fixed size. Important thing. This is a rigid body mass matrix. So it's 6 by 6 in 3D, 3 by 3, 2D. And the bottom line is that every one of these steps in the recursion, we're always just inverting like a 6 by 6 or a 3 by 3. It's a fixed size matrix that doesn't change ever, right? And similarly in the S equation, which I will now attempt to copy and paste. So this guy, same deal. I'm solving a linear system over here. Here's this, this like linear system you got. How big is that one? So this is a joint constraint thing, right? And depends on what kind of joint. But in what we're doing here, these are all revolute joints. If we're in, and they only have 1 degree of freedom left. So if I'm thinking about it in 3D, what size does it have to be? In 3D, got to be 5 by 5. In 2D, it would be 2 by 2, right? Because it's taking the rigid body and like removing all the 1 degree of freedom, right? So this would be like 5 by 5 in 3D or 2 by 2 in 2D. So the main message is that all of the linear systems that you have to solve in that recursion are of fixed size, of like it's a few. And they're small, right? So I'm talking, if I have a giant robot, like it's like 5 by 5, 6 by 6 matrices. These are trivial to invert, right? So this is very fast and cheap. Cool. So for an n-link system, think about n links in this pendulum thing. I've got n of these little systems, right? To do in my recursion. So what that looks like, if I were to like write this all down, it's something like, say 6 cubed plus 5 cubed times n lengths. So the dimensions of those little guys just falls out of this as just a constant. So this is just order n. Right? Everyone agree? Cool. So we got this down to linear complexity instead of cubic. That's pretty neat. Cool. Yeah, what else should we say about this? Okay, so this linear time thing is like, you've heard of this, right? You've heard of it in many, many contexts. This is just like showing you the actual mechanics of like how this gets done, like where it comes from, etc. You do it yourself for your own weird problems. Maybe you can do one of these for something weird and someone will name it after you. Happens a lot apparently. Okay, so yeah, like some more commentary on this. So this is linear time. We did it for this really simple, just like totally, linear like serial chain thing. You can actually keep the linear time complexity for things slightly more general than that. So let's say the following thing. It's generally possible to achieve this order n complexity for any systems that are so-called like open kinematic chains. And this can be, pretty weird things in general, like, you can have lots of branches on these guys. So we could have links popping off from each other like this, and, all kinds of weirdness, right? So this is totally illegal. The only thing we can't have are closed loops where one of these guys comes back around and hooks back up to a parent. So, and we'll show you kind of why that's a problem. So and what I mean by closed loop is if I have, say, something that looks like this. So if I were to and I could have weirder stuff over here, but if I come back around and say connect back over here to a parent link, that forms a closed loop. That is bad. Why is that bad? Let's write down the Jacobian thing. So if I have the big constraint Jacobian and I were to write the block structure of this guy, I've got some nice structure in general, like before, where I might have something like, so if this is, connected to a ground, like before, I'll have like this kind of deal. And then I've got a bunch of, serial chain type stuff that does this kind of thing, like we saw, maybe, whatever. So let's say, I don't know how accurate my cartoon is, but let's say we've got like 5 links, something like this, but then let's say this guy loops back around, hooks back up to link 1. What does that look like here? So we've got a constraint 6, so it's a new row. And which links does it couple? Couples, say, link 5 and link 1. So if I look at the block structure now, I'm going to end up with something that looks like this: link 1, constraint 6, and then say link 5, constraint 6. So now my sparsity pattern is sort of broken. I no longer have a nice banded matrix, and I no longer am able to do my sweet little back substitution trick. So I'm now getting like fill in off the band, right? The band thing is key. The banded structure is what makes all this work. So I'm now no longer banded. And that's that. Okay. What else do you guys want to know about? So what else? Okay, so I was going to talk a little bit about the sort of how you get to the RNA stuff from here. So this is all maximal coordinates, obviously. This is honestly kind of the natural setting to do this stuff in, because the maximal coordinate stuff exposes this. Like, this is just structure in that KKT system that you can see and then play games with, like we just did. In minimal coordinates, which is like where Featherstone is kind of lives in RNA and all those things, you just have a dense mass matrix, and it's not at all obvious that there's some structure to play with there. So what do we do? Like, where do you get that from? If I sort of showed you this trick and then was like, how do you do this in minimal coordinates? What would you do? That's the right idea. Yeah. So we talked about how you get that dense mass matrix from this kind of thing. So if you blow that up and you get the diagonal guy and the block structure constraint Jacobian thing, that's basically the pieces of this guy, right? So in fact, that thing's what's called a Schur complement of this KKT system. So yeah, basically what you want to do is sort of come up with a mapping between this picture and the minimal coordinates picture. The way you do that, how do I get from minimal coordinates to this? What's that called? If I give you the minimal coordinate state, like a bunch of joint angles, and I ask you for this big state, what do I do? Forward kinematics, right? So I can do forward kinematics, and then I can also compute all these Jacobians, right? So basically, I can map from minimal coordinates to this guy through the forward kinematics, and then basically do this recursion. And I can obfuscate that by burying this recursion in a bunch of like constrained Jacobian stuff and sort of projecting it back down. And that's essentially what the RNA algorithm is doing. It's sort of hiding this nice clear picture in a bunch of garbage, and they sort of derive it a different way, but you can easily get it from here. And that's really what's going on. If you do that, what you get is exactly, if I did that here, what you get is exactly the Riccati equation from control from LQR. So like the RNA thing is literally the Riccati equation. We're not going to do that though. It's sort of, but that's exactly what it is. So what ends up happening, just fun facts, we're kind of done. The forward pass from like a sort of control problem ends up being your forward kinematics. Like if you imagine like ILQR, you guys do controls, the forward rollout is your forward kinematics, and the backward pass is this backward recursion that we just wrote down. And those like W and S things end up being like the cost to go things from LQR in the Riccati equation. Okay, so the missing piece of today is the code demo, which is broken. I was trying to get it to work on the plane. It is almost working. So I did this. Here it is. Here's all my horrible debugging. But I will fix this as soon as I get some sleep and can think straight, and I'll send it to you guys.
Just curious, for the cases of closed loops, are there?
What do you do? So it depends. Basically, what you can do is, let me throw this back up here. So what you actually do in practice, you still be kind of smart. So if I like, let's say I have something that like I cartoon draw where it's like, you know, a whole bunch of serial things, and then you have like a, so when you say efficient, right? Like absolutely, simply because like this thing's still sparse, right? It's not a nice banded matrix, but it's still a sparse matrix. So there's still stuff you can do. It's not going to be order n anymore. But what you can get to happen here is I can play nice games where I basically like, I can permute this matrix, right? I can always permute rows and columns and stuff like that and kind of move things around. So what I can basically do is squish things around. So I like squish this guy into like one of the corners. So what I basically will do is I'll take all my closed loop badness and I'll squish it into one corner of this matrix such that the rest of it is like the nice serial chain part. I'll do my factorization that we just talked about until I get to the nasty closed loop block. And I'll basically like do the nice linear time thing until I get to the closed loop block, and then basically kick out of this special factorization and do a more generic like dense matrix factorization on the block that's left that has the closed loop part. So generally speaking, what you can get this down to is like linear in everything except the closed loop block, and then a cubic part, but it's only cubic in the size of the closed loop. Does that make sense? So it's still more efficient than a naive implementation. And you can write down the complexity of that, and it's still better, and it's, you know, efficient. But that's basically the best you can do in that kind of situation. There are other things you can do, but I think the main takeaway here is that the way to get at this efficient, fast stuff is by like having this picture in your head of this sparse matrix stuff. I would argue this is like the natural way to, this is just where the structure shows up, right? If you do the dense minimal coordinate thing, just not there. You don't see it, and you have to like sort of figure out other ways to get at it. Here, it's just obvious and staring in the face. You can do lots of other things though. Like now we're just doing sparse matrix math, and there's tons of nice algorithms in general for general sparse matrices that are maybe unstructured, right? In particular, there's like indirect linear algebra. So if you had a gigantic one of these for some like say continuum model, right? Like in the limit of like, so like this, you know, serial thing, like a big long pendulum. In the limit of like a continuum, this model's like a beam or something, right? So if you had say you had a giant FEA model of a beam, it's going to have the same band structure, and you could use it for that too, right? But if it's really, really big, say, and you have some weird stuff in there, and you don't want to do this direct recursive stuff, you could, for example, use a generic indirect linear algebra solver like conjugate gradient or something along those lines to still solve this very, very efficiently with much less than cubic complexity. So there's like lots of ways to do this. I showed you one way that's basically the same as what the RNA stuff is, but you can like sort of do your own thing. Yeah.
Like, RNA solving the inversions and the ADA self-sorting.
Maybe that's right. I don't know. They're all the same idea. Yeah, I don't know what those acronyms. I don't know.
ADA, sorting.
Okay. Yeah, I don't particularly care. Like, this is the actual insightful thing. This is where it comes from. You can derive any of those things that you want from like this thing. They're just like various tricks for solving a sparse matrix. Okay. So like all of these recursive, dynamic linear time dynamics things are doing this under like at some deeper level, they're all just doing this. And they call it different things and they dress it up with weird notation and like whatever, but this is what they're actually doing.
This is also what you're using when you formulate the problems as sparse matrices.
So I mean, Julia has, so what we did is, so I would say no, in general, if you like set up a generic sparse matrix and use some sparse matrix toolbox, they're not doing this. This is much, much faster than that actually, because what we did is like, we know the sparsity pattern ourselves. So we, the way we wrote this down, right, in terms of the S's and W's, we're only ever storing the dense little blocks inside here. And we're doing all dense matrix math on little like 6x6 or 5x5 or whatever size matrices, just blazing fast, fits in cache, et cetera. What you end up with in like a generic sparse matrix toolbox is it's actually storing like a key value pair kind of data structure where it's like index, IJ equals number, index whatever equals number. It's like a lookup table, like the entry wise. And basically the story there is like those things are only like worth it and fast for extremely large, extremely sparse matrices. For something like this, that's maybe, like, I don't know, worst case for a robot, like maybe 100 dimensional or so, right? A couple hundred dimensions. That's actually small by sparse matrix standards. Like when people like talk about that stuff, they're talking about, like potentially like millions of dimensions on like gigantic optimization problems and stuff like that. This is kind of small potatoes by those standards. And if you tried, like you could absolutely set this up as a sparse matrix in Julius A or whatever, but because of the way those data structures work, that they're basically storing these like key value pair kind of things in a data structure, they're just inherently way slower than this, because what this is doing is dense linear algebra on these little blocks, which is stupid fast and like fits in cache on your CPU and stuff. And you're not doing this like key value pair lookup stuff for each entry, right? That makes those generic sparse matrix things really slow. There's a lot of overhead. Here, there's like no overhead. It's a for loop and a bunch of dense tiny matrices operations, right? That's the story. Okay. I think that's it, guys.